All right, so whoops, we're going to go ahead and continue with this example and start on part C. So we need to check and see if this is true for this one as well. So let me go ahead and start on a new page. Ooh, that's red. I would like white. Makes it a little easier to read. Let's see, white. Okay. So part C, we have, I'm going to go ahead and copy it down, ax sub I plus, sorry, I hat, plus ay j hat over x squared plus y squared. Okay. So when I'm taking derivatives like this, where there's something in the numerator, I like to rewrite it, so I'm going to go ahead and do that. So I'm going to say ax times x squared plus y squared to the negative 1, I hat, plus ay x squared plus y squared to the negative 1, j hat. Okay, so we first want to do df sub x dy. So that's this first term. So we get the first, right, times the derivative of the second, which is going to be negative 2 times x squared plus y squared, negative 1, I'm sorry, negative 1. Okay, I hat, or I'm sorry, ignore that. So first times derivative of the second plus the second. Oh wait, no, because we're just doing it with respect to y, right? So give me 1 second. Let me erase some stuff, making it more complicated than it needs to be. All right, so we have that, and then we need to take the derivative of the inside, which I forgot to do. It's going to be 2y. Okay, so we have negative a 2a x y over x squared plus y squared, and this is squared. Okay, now let's do df sub y dx. Okay, so we have ay minus x squared plus y squared to negative 2. Take the derivative of the inside, that will be 2 times x, and that gives me negative 2a xy over x squared plus y squared squared. So these two are equal. This means that this force is also conservative. Okay? All right. So let's go ahead and move on now. Talk more about potential energy. So non-conservative forces don't have potential energy associated with them, since their work is lost to the system and can't be returned, can't be turned into useful work later. Okay, so the infinitesimal increment of potential energy is then du equal negative f dot dl, where dl is going to be the distance, okay? And that equals negative fl dl, or we can say f sub l is equal to negative the derivative of potential energy with respect to L. Okay, so now what we can do is we can rewrite this force in terms of potential energy. So force vector is going to be f sub x I hat plus f sub y j hat, or equal to negative del u del x I hat minus del u del y j hat, where the del's here are partial derivatives. So partial, whoops, derivatives. Okay. Now let's go ahead and do an example. The potential energy for a particle undergoing one-dimensional motion along the x-axis is u of x equals 1/4 c x to the 4th, where c is equal to 8 Newton per meter cubed. Its total energy at 0, x equals 0, is 2 joules. And it's not subject to any non-conservative forces. Okay? So find the positions where its kinetic energy is 0. Okay? So that's our first task here. So we have u of x. I'm going to just write it again. 1/4 times c x to the 4th. Okay? So that's our potential energy. We want to know what position where kinetic energy is 0. Okay. So let's go back. We have W. No, we have U. I'm sorry. No. Okay. So we have this instance here. So let's see. Oops. Total energy K E is equal to U plus K, right? So what we need to do is say that at this point we have the kinetic energy is 0. Okay, so then our total energy is going to be, let's see, if this is 0, our E should equal U, okay, or our total energy, and we can determine this relation by using this point here, where we have 2 joules, then will be equal to 1/2 8 Newton per meter cubed times x to the 4th. Okay. So we have, oops, this is to the 4th. We have then that x to the 4th is equal to 1. And this will be joules, meters cubed over newtons. Okay, so then x will then be either positive or negative 1 meter. Okay. All right. So then we want to know what the forces are at these positions. So we just learned that force is going to be negative du dl. So F is going to be negative du over, in this case, it'd be dx, since we just have it in one dimension. So we'll take the derivative here, and that will give us, let's see, 2 times 4x cubed. Okay. And so we'll have negative 8x cubed, and so F at positive 1 meter will be negative 8 newtons. F at negative 1 meter will be positive 8 newtons. Okay. I did forget to mention the direction that this is in. This is in our x-axis, or positive x-axis, so I'll go ahead and put I-hats on these forces. Okay? Alright, so moving on to conservation of energy. The main idea here is going to be that the energy we have is neither created nor destroyed. Okay? So that's going to be a big idea, and you've probably heard that before. So the mechanical energy, E, we'll call it, of a particle stays constant unless forces outside the system or non-conservative forces like air resistance or friction do work on it. And in that case, the change in mechanical energy is equal to the work done by the non-conservative forces. Okay, so that's what NC is. That's non-conservative. Okay. So, this is the concept of conservation of energy for a classical particle, and that is as long as there is no non-conservative work. Okay? The mechanical energy of a particle doesn't change if all the non-conservative forces that may act on it do no work. Okay? So, our work done by non-conservative forces from A to B is equal to 0, and is equal to the change in our mechanical work, or mechanical energy, I'm sorry. Okay, so let's go ahead and look at a problem-solving strategy for this section. First, we want to identify the body or bodies to be studied, so the system. We want to identify all forces acting on that system, or systems. Determine whether each force that does work is conservative. If it has a non-conservative force, like friction, that is doing work, the mechanical energy is not conserved. Okay, so we do need to note that. For every force that does do work, choose a reference point and determine the potential energy function for that force. Okay, then we can apply the principle of mechanical energy conservation by setting the sum of kinetic energies and potential energies equal at every point of interest. Okay, so remember, mechanical energy is equal to change in kinetic plus change in potential. Okay, and that's what we've been using all along, but we didn't put a name to it until now. Okay, so let's go ahead and start on an example. A particle of mass m is hung from the ceiling by a massless string of length 1 meter, as shown here. The particle is released from rest, and the angle between the string and the downward vertical direction is 30 degrees. Okay. What is its speed when it reaches the lowest point of the arc? Okay, so that would be at h here. So we want to know its speed. Whenever we will want to know speed, it's going to be related to kinetic energy, right? So kinetic energy is 1/2 mv squared. Okay. So we'll need to use the conservation of energy idea in order to solve this. Okay, so we've got energy is equal to the change in kinetic plus the change in potential. Okay, let me go ahead and stop here, and we'll start on the next video. We'll continue this problem.